In this video, we're going to look at one of the most widely used methods for determining a non-informative prior, and that is the Jeffreys prior. Now, to calculate the Jeffreys prior distribution, we first need to review the definition of Fisher information. So if we have our sample data here with a common distribution that depends on our parameter theta, then the Fisher information is what we see here. So recall how to compute the log likelihood function. So remember, with likelihood, that's where we treat the data as given and the theta as variable, which is evidenced in the fact that we're taking a derivative with respect to theta. And then once that log likelihood function is determined and this partial derivative is taken to obtain what's called the score function, then we can put back in the big X and then take the expected value, now treating theta as given and the expectation with respect to our data. So there is a lot going on there. So hopefully at this point we're comfortable enough with log likelihood and the difference between that and PMFs and density functions that this makes sense to us. And we will do some examples. Now this is assuming that theta is just one real parameter. If we have a vector parameter, or we define what is called the Fisher information matrix, which we see here. So this matrix is a P by P matrix. So it's a square matrix with common dimension that matches the number of elements of our vector theta. And we define what goes in the ith row and the jth column of this Fisher information matrix as we see here. And this expression can be interpreted in a similar way to what we saw earlier. Right, and we have to first calculate the log likelihood and then take the derivative with respect to theta I, and then whatever you get from there, now you're going to end up with some little x's, and wherever those are, we're not going to make those a big x's. And similarly here, and then take the expected value with respect to the data. As it turns out, directly applying the definition can sometimes be difficult, but there are situations where we have a different formula that is a little bit easier to work. And so in many common situations, it can be shown that these formulas here are equal. So these are computational formulas that apply in, like it says here, in many situations. Okay, now once we have an understanding of how to calculate the Fisher information, then we can look at what's called the Jeffreys prior. And so given our sample data that depends on a single real value parameter, then our prior distribution is going to be proportional to the Fisher information raised to the 1/2 power. And then in the situation where we have a vector parameter, then the Jeffreys prior is proportional to the determinant that you see there, right? We first calculate the Fisher information matrix, then we calculate its determinant, and then whatever that is, we raise to the 1/2 power. In this example, we're going to be given one observation from a binomial distribution with parameters little n and theta. Here, theta is our unknown. And we're going to determine a Jeffreys prior for that theta. To do that, we've first got to calculate the Fisher information. And so, since we only have one observation, then we look at the PMF. But we're going to consider x as being given and theta as our variable. So we're really looking at this as a likelihood function. And so from there, we're going to calculate the score function. And remember that to calculate the score function, we first have to take the log of the likelihood function. That's what we see here. And then we calculate the derivative of that log likelihood with respect to theta. Now at this point, I want to point out something that's true in this particular instance and which is true in general. Notice what I've done here is taken the score function and replaced the little x's with big x's. So now they're back to random variables. And we're going to treat theta now as given and take the expected value with respect to our data. Also notice that we have substituted in the expression for the score function, and the expected value here is in theta, again since this x is a binomial random variable. And then if we use the linear properties of the expectation operator and just apply a little bit of algebra, what we see is that the expected value of the score function is 0. So what that tells us about the definition of Fisher information is, well, let's see. Here is the definition, and of course this inside part is the score function. Notice we've got the big X there, and we're squaring it and taking the expected value. And also, in our situation, the mean of the score function is 0. So for our function, at least, what we're talking about is the variance of the score function. And I will tell you that what is true for our example is true in general. It is true. The expected value of the score function is always going to give you 0. So the Fisher information really is just the variance of the score function. Which is what I have written here. But now remember, we also have the computational formula, and that's what we're going to use because it's easier. Right, so we're using this formula here. Now we're back to little x here, and we need to calculate this derivative. The second derivative, in fact, of the log likelihood function with respect to theta, and that gives this. And so finally we're able to calculate the Fisher information. So at this point we're going to plug back in big X's here and treat theta as given and take the expected value. And remember that formula had the negative in front. And so we have this, and then taking the expected values and simplifying, we see that the Fisher information for this problem is what you see here. Having now arrived at the Fisher information, we can now apply the formula and calculate the Jeffreys prior. So remember that the Jeffreys prior for theta, the formula is that it is proportional to the information, the Fisher information to the 1/2 power, so that gives us this. And then if we simplify, we see this expression here. And the thing we have to try to do is determine what particular distribution is this pointing us to. And the first thing to note, and this is really important, is that theta here is a proportion, so it's got to be some distribution concentrated on the unit interval from 0 to 1. And it's got to be some constant, right, times something that looks like this. So this is where our distribution sheet is going to be so useful. Okay, here I have pulled up the distribution sheet, and these are the continuous distributions. So the thing we have to concentrate on is the fact that theta has to be in the interval from 0 to 1, so we need to look at distributions that are concentrated on that unit interval. And so that should bring our focus to the second one as a possibility, the beta distribution. And that's the one that we need, right? Because if you look at the variable part, it's x to the alpha minus 1, and in this instance we need to think of x as where theta is going to go. So we've got theta to a power times 1 minus theta to a power, and that fits perfectly. The only thing we need to do is figure out what is alpha and what is beta. And perhaps the easiest way to do that is just to look at that first power on x, alpha minus 1. So whatever the number is, you just add 1 to it and you get alpha. And then similarly, the power on 1 minus x, you add 1 to that, and that gives you beta. So if we apply that to our problem, then each one of those powers in this case is negative 1/2. Add 1 to both of those and you get 1/2. And so that is how we identified that this is pointing us to a beta distribution with parameters 1/2 and 1/2. And that is the Jeffreys prior. So if we want to determine the normalizing constant, then we can just look back at the distribution sheet, and you'll see the form of the normalizing constant. It's the numerator is gamma of alpha plus beta, and then that's divided by the product gamma of alpha times gamma of beta. And so that's how we get 1 over pi. So therefore the Jeffreys prior for this situation is what we have there.